Welcome back to this lecture series on deep learning. In this lecture, we'll see CNN learning in that what is the role of activation functions. First, all we should know activation functions or why we are using activation functions in CNN. The activation functions are essential because they introduce nonlinearity, allowing CNNs to learn patterns that simple linear layers cannot capture. They help the network recognize complex image features such as edges, textures, shapes, and objects. Without activation functions, deep CNNs would behave like linear models. If you are using linear models, what will happen means it will be losing their ability to learn meaningful representations. Understanding activation functions helps us design more accurate, deeper, and efficient neural networks for real world applications. We'll see one by one. First, the role of activation function. The key idea behind this by using this activation functions or a convolution neural networks. The networks, a convolution neural network that is CNNs, without an activation function. Without an activation function, it will behave just like a purely linear systems, no matter how many layers it has. Even if we stack multiple convolution layers, the entire network would still perform only a linear transformation similar to a simple linear regression model. Because of this, the network would fail to learn complex visual structures found in images. Activation functions introduces nonlinearity and essentially introduces the essential nonlinearity that allows the CNNs to understand and model intricate patterns such as edges, corners, textures, and repeated shapes, object contours, and even high level concepts like phases or objects. Without activation functions, the convolution neural networks would not be able to differentiate between different visual classes, making them ineffective for real world tasks. So, if you want to use the real world applications, compulsorily we have to go for the activation functions. How nonlinearity functions are used in CNNs. Why we should need nonlinear functions? Nonlinear activation functions are important in CNNs because they allow the network to learn relationships that cannot be represented by linear operations alone. After a convolution and a polling layers, extra local and spatial transformation, nonlinear activations helps transform these features into deeper and more abstract representations. This enables the CNN to build hierarchical learning starting from simple patterns like edges and moving to textures and small regions and ultimately recognizing the entire objects. Nonlinearity ensures that the network can perform complex tasks such as image classifications, object detection, and face that is segmentation, etc. And in this case, what it will do is it can perform the complex tasks naturally, what I said, classification, object detection, and segmentation, that is medical image analysis and semantic segmentation. Without nonlinear activation functions, the CNN would be unable to map inputs to meaningful outputs, severely limiting its learning capability. So we'll see one by one all the nonlinear activation function. These are all the nonlinear activation function. Rectified linear unit that we are calling it as the ReLU. Next, leaky ReLU, parametric ReLU, P ReLU, exponential ReLU, ELU, scaled exponential linear units, SELU, we can call it as hyperbolic tangent tan H and sigmoidal function, then the Swiss function. We'll see one by one. The rectified linear unit, here the output is founded by f of x. The f of x is the output, maximum of 0 comma x. See, if you are finding out the values, net input x is the net input applied to the neuron. Here the negative parts are equal to 0, only we are getting the positive part. So that only we are writing the function f of x equal to, how we are writing, maximum of 0 comma x. And here most commonly we are using it in the hidden layers of the deep networks. The advantages of using the ReLU functions are it is simple, fast, and reduces the vanishing gradient. Even though it has got many advantages, it has got drawbacks also. Dying ReLU problems. Some neurons stop updating. So this is the graph of the ReLU functions. Next, leaky ReLU. Here we are going to take f of x equal to maximum of alpha x into comma x. Alpha is the learning rate 0.01. The value is and here the variations of ReLU that allows smallest gradient for x is less than equal to 0. The advantages of using leaky ReLU is solves dying ReLU to some extent. Here, see here, some difference is there comparing to the previous one. Here, flat, and in this case, some leakage is there in the negative. This is the graph of the linearly leaky ReLU function. Next, the parametric ReLU function, P or P ReLU, we can call it as the functions like it is like a leaky ReLU, but alpha is learned training rate. The deep neural networks where more flexibility is needed. This is the function. Here, somewhat it is being varied from the ordinary ReLU. This is called a parametric ReLU function. The next one is the exponential linear ELU, and the function is given by x if x is greater than or equal to the net input applied to the neuron is greater than 0, we are going to get x. Otherwise, x is less than 0 means we are going to get alpha into e to the power x minus 1. And here it tries to bring mean activations closer to 0. This is the function of that ELU function. ELU means exponential linear unit. Here it has been given like this. Next, ZELU functions, scaling linear activation functions. The scaling parameters used in this case are the variants of ELU that applies additional scaling parameters to maintain the self-normalizing properties. In order to maintain this property only, we are going to use this scaling parameter techniques. We are going to use it. This we can call it as this is self-normalizing, improvising the maintaining the self-normalizing function. And the ZELU keeps the mean and variance stable. This is the biggest advantages of the ZELU as the signal passes through layers, and it works best with the self-normalizing neural networks, SNNs. The advantages of using the ZELU function is it enables very deeper networks and it maintains internal normalizations automatically. So this is the function. So comparing to the previous case, the graph would be like this. This is the ZELU activation function. And the hyperbolic tangent functions f of x is given by tan h of x e power x minus e power minus x divided by e power x plus e power x. Here these x's and all, it is not an input, net input applied to the neuron. And the output value is between minus 1 and 1, and it is better than the sigmoidal function in the hidden layer. These functions mainly we are using it in the hidden layers, and even though it has got advantages, it suffers from the vanishing gradient. This is one drawback of this tan h. So this is the function, tan h function. We have got both positive and negative things, or there both and the final one is the sigmoidal function, very very important function, and the f of x is given by there e power x minus e power minus x divided by e power x plus in the tan h, but here 1 divided by 1 plus e power minus x. The output varies from 0 and 1, and it is used for drawbacks vanishing gradient and not zero centered. See, it is not a zero centered, so that only we can call it as it has got some drawbacks. And the Swiss function, it is given by x into sigmoidal of x. See, we have to find out this value, and also we have to multiply this x. Net input x means net input applied to the neuron, and it is proposed by Google, and it can outperform the ReLU on the deep neural networks. If the hidden layers are maximum, we can able to use this Swiss function. So here the values, here somewhat it is been differing, and the graph going like this. So hope everyone understood the basic activation functions. It is used for the nonlinear if you are using in the deep neural networks. I have given deeply the brief explanation in the previous lectures. I'll be giving you in the description box. If you want to learn more things, you can refer my the link what I'm given in the description box. Hope everyone understood. The remaining things we'll discuss in the next class. Thank you.